Hello BGC float enthusiasts, my name is Yui Takeshita, and today I will be walking you through nitrate measurements from BGC profiling floats. And this talk is part of the Go BGC Science Workshop that is starting on June 28th, 2021. And this video is meant to be a little bit more of a deeper dive into the specifics for nitrate measurements. I want to start this talk by showing you a short animation that shows the locations for all of the nitrate floats that have been deployed so far. All this data was taken from the Argo Data Assembly Center. And as you can, and the plot behind the animation shows the number of float nitrate profiles per year over the same time period. And as you can see, the number of nitrate profiles per year have been steadily increasing over the past 10 years or so. And GoBGC, which started in late 2020, our first 12 floats were deployed earlier this year, and in the North Atlantic, shown in the pink box. And we are funded to deploy 500 more floats, all equipped with nitrate sensors over the next 5 years. So we anticipate that the number of float nitrate profiles is going to substantially increase over the next couple of years. And in addition to GoBGC, we also anticipate international partners to continue deploying profiling floats with nitrate sensors as well. So that will further increase the number of nitrate profiles available from floats worldwide. So we're really hoping that people will take advantage of this data set. And the point of this workshop and this talk today is to arm the community with the tools that they need to take advantage of this upcoming data explosion, essentially. So let's get started. So this is the outline of my talk. I'm going to start with the technology of nitrate sensors, so basically how sensors work and how they're configured. Then I'm going to follow with a little bit with sensor calibration, and then finally how size quality data are generated from profiling floats, which include an important data adjustment step, and then how the data adjustment are validated through bottle measurements. So before I would also like to mention that most of the information that I'm going to present in this talk is included in this Argo data management document, processing bioargo nitrate concentration at the DAC level. So if you're interested in the nitty-gritty details and exactly how to implement the calculations, all the information that's necessary is in this document, including MATLAB code, check values, and things like that. So if you're really, if you're curious and brave, I would encourage you to take a look at this document for more information. Okay, so nitrate sensors, they work by measuring absorbance of seawater. So absorbance basically works by shooting light through seawater, and as light goes through seawater, certain compounds interact with light and absorb the light. So the incoming light, there's more light coming in than out, and then which is described in these arrows here. So I naught is the intensity of light at any given wavelength that's coming into seawater, and I is the outcoming light intensity after the light passes through seawater, and some of it was absorbed. And then the absorbance is calculated as the log of the ratio of these two terms. And to get concentrations of certain analytes that you're interested in, for example, nitrate, absorbance is related to the concentration through the Beer's law, which is shown here. So absorbance is equal to the molar absorptivity, which is epsilon, multiplied by the path length, which is B, multiplied by concentration, which is C. So for any given instrument, the epsilon and B we can treat them as constants, and therefore the absorbance of any given wavelength is proportional to the concentration of the analyte that you're interested in, for example, nitrate. And there are basically two nitrate sensors that are currently deployed on profiling floats. The first is the ISIS, or the In Situ Ultraviolet Spectrophotometer. And this was the sensor that was originally developed by Ken Johnson at MBARI and later integrated onto profiling floats in collaboration with Steve Reiser at the University of Washington. And so you can see the schematic of the ISIS that's integrated onto the Apex float end cap here. And so ISIS sensors, as a result, are only deployed on profiling on Apex floats that are made in collaboration between MBARI and University of Washington. But this technology was licensed to Seabird and commercialized so that it became available for the rest of the community. And the nitrate sensor that Seabird sells is called the Suna. And then so all other profiling floats such as Navis, Provor, and the soon-to-be deployed BGC Solo 2s will all be equipped with Suna nitrate sensors. And as you can see, the Suna sensors are not integrated into the float end cap, but rather they're kind of standalone sensors and bracketed to the side of the profiling float. And they establish power and communication with the float controller through an underwater cable. And it's important to note that these sensors are basically the key components for the sensors. So the lamp and the spectrometer are identical between the ISIS and Suna, and the difference really is in their optical setup, which I will go into right now. So the ISIS on the left uses a retroreflection probe to measure absorbance of seawater. So a zoom in of the probe is installed at the top of the end cap, and the zoom in of what the probe is shown here. So basically you can shoot light from the lamp inside of the float housing, and then it goes up a fiber optic cable, and the light shoots through the seawater, bounces off a mirror, and comes back down through another set of fibers and into the spectrometer. So this is how the ISIS measures absorbance in seawater. Suna, on the other hand, has the lamp and the spectrometer in different parts of the housing, and the light just goes through from one housing to the next. So this is, these are the differences between the optical setup between the two sensors. But because the critical components of the sensor are identical, the performance of the two sensors are comparable in the field, which is good news. Okay, so let's dive into the details now. So this is the absorbance spectra for nitrate if nitrate concentration was at 50 micromolar. So as you can see, nitrate absorbs in the deep UV between about 210 and 240 nanometers. And if nitrate was the only compound that absorbed in this wavelength range, then it would be very straightforward. You just make the absorbance measurement, and you use Beer's law to calculate what the nitrate concentration is, and you're well on your way. But unfortunately, other compounds also absorb in the same range and contribute to the overall measured spectra. And the dominant signal actually comes from bromide, which is shown here in white. And so this is absorbance spectra for bromide if salinity was about 35. So as you can see, bromide absorbs a lot more than nitrates, particularly in wavelengths shorter than about 220 nanometers. So this becomes a dominant signal. On top of that, there's another component that absorbs in the UV, which is dissolved organic carbon, or DOC. And we parameterize DOC as just a linear absorbance spectra that ranges from 210 to 240 nanometers. And this has been shown to be the case in the literature. So when you actually measure the absorbance of seawater, it's the sum of these three components, which is shown in the pink here. So, the measured absorbance is the sum of bromide, nitrate, and also the linear contribution from DOC. So the challenge really the challenge really is how to separate or deconvolute these three components from the overall measured absorbance. So if you measure this absorbance, how do you know, how do you break it apart into the three components that contribute to it: bromide, nitrate, and DOC? And the initial algorithms that were tested try to simultaneously fit all three spectra to the measured absorbance. And this worked well for most of the time, but sometimes it led to overfitting or overcompensation of certain spectra and led to negative nitrate concentrations, which we know is not possible. And this is kind of the Three Stooges problem. When you try to fit all three spectra at once, or Three Stooges try to go through the door at once, you don't get the best results. So how do you get around this Three Stooges problem? Well, we take advantage of the fact that you can actually calculate the concentration of bromide from salinity. And since absorbance is related to the concentration, if you know salinity, then you should be able to calculate what the absorbance spectra is for bromide and then subtract it out from the overall measured absorbance spectra. And then that will leave you with only trying to differentiate nitrate and DOC, which would substantially simplify the situation. So, but you need a little bit more information than just salinity to do this. And specifically, that's because the absorbance spectra for bromide has a temperature and pressure component to it. So this is the absorbance spectra for bromide if for salinity about 35 at 20 Celsius and 0 decibars. But in the same solution, salinity at 35, but the temperature was decreased to 2 Celsius, now we can see that the absorbance of bromide decreases significantly. In addition, then now if you increase the pressure to 2,000 decibars but keep the temperature the same, pressure further decreases absorbance by about 2.6% per 1,000 decibars. But the good news is, if you know temperature, salinity, and pressure, then you can actually calculate what the bromide spectra should be. And then once you calculate what the bromide is at in situ temperature, salinity, and pressure, which is routinely measured by the CED, then you can actually subtract out the bromide component from the measured absorbance, and then now you are left with just fitting two spectra to the overall measured absorbance. And so you can break this into a fairly straightforward linear equation where the measured absorbance with no bromide is equal to an intercept term and a slope times wavelength. So this is the DOC component shown in orange, and then the nitrate component, which is the nitrate concentration multiplied by the molar absorptivity of nitrate. And I should mention right now that the DOC component also takes care of any shifts in the baseline or the performance of the lamp itself. So for example, if the lamp intensity changes due to temperature changes or aging, the DOC component largely takes care of that, because these shifts in the lamp intensity manifests as a change in the intercept or a constant offset in the absorbance. So by the intercept will basically take care of that for such drift. So how do you calibrate these instruments? So in order to calibrate, the calibration process basically consists of quantifying three terms. The first one is the I naught term shown on the top left here that's needed to make the absorbance measurements. And the I naught measurements are measured for each sensor in deionized water. And we measure this in deionized water because we need to measure the absorbance of bromide. So we need the blank to be in deionized water. The second component we need to quantify for each sensor is the bromide spectra. And basically, so for each instrument, we measure the molar absorptivity of bromide in low nutrient natural seawater. So we measure the salinity of the natural seawater and calculate what the bromide concentration should be, and then quantify the molar absorptivity for bromide for each sensor. And we define the molar absorptivity in a way that makes it easy for people to calculate what the absorbance of the bromide would be. And basically, in order to calculate what the absorbance is, you multiply the molar absorptivity of bromide by salinity, and then correct it for temperature and pressure. So in other words, the molar absorptivity of bromide that's determined in the calibration process is basically what the absorbance of bromide would be when salinity is equal to 1. And the final component is the quantifying the molar absorptivity for nitrate, and we take a similar approach for bromide. So we measure the nitrate, the molar absorptivity of nitrate in the same natural seawater, but with known amounts of nitrate that's added. So it's kind of like a standard addition approach. And then we also define the molar absorptivity of nitrate as basically what the absorbance would be if nitrate concentration was 1 micromolar. And this is a picture of what the calibration setup looks like at MBARI for calibrating an ICIS sensor. So the ICIS probe sticks out of the float head, and then there's a flow cell that goes over the probe that's temperature controlled, and also you can push different fluids or different solutions through the green peak tube that you can see that's coming in and out of the calibration cap. And the whole system is put under a slight pressure so that it avoids the formation of microbubbles, since these sensors are very, very sensitive to any bubbles that may form in the optical path. Okay, so now once you have the sensors calibrated, you can equip them on a float, and they can start to make measurements profiles in the ocean. So, and this is what a nitrate profile may look like in the ocean. And this is a profile from an Apex float using the ICIS. And as you can see, the sampling resolution is not uniform across the whole water column, and it ranges from about 5 meter resolution in the upper water column to about 100 meters every 100 meters below 1,000 meters. And this is because this is really largely driven by the power requirements of the nitrate sensor, and and if more samples were taken per profile, then it would significantly eat into the overall power budget of the float, and therefore it would lead to a shorter lifetime of the float. So there's a trade-off between the vertical resolution that's made by the nitrate floats to the longevity of the floats, and we have settled in making about 70 measurements throughout the water column from about 2,000 meters. And the sampling resolution is fairly similar between SUNAS and ICIS. But that leads to a slight complication in that the CTD and other biogeochemical parameters potentially have a higher vertical resolution than the nitrate, which means that different parameters are on different pressure grids. So, recent profiling floats are equipped with continuous CP mode CTDs, or continuous profiling mode CTDs. They measure temperature, salinity, and pressure every 2 meters in the upper 1,000 meters of the water column. So then this mismatch between the nitrate pressure grid and the CTD pressure grid adds another barrier or another complication for anyone who wants to use the data. Fortunately, we have done the work for you to merge these different data streams into a uniform or the same pressure grid. And then you can access this data through the SPROF files on the Argo data center. So anytime you download BGC float data from the Argo data centers, please use the SPROF files, because all of the SPROF files have already merged the different BGC float data into a uniform pressure axis. And for more details, you can look at the data management talk in the workshop for more details. Okay, now moving on to the data adjustment and validation part of this talk. And data adjustment is a very important part of any BGC float operation because biogeochemical sensors are more prone to sensor drift and calibration offsets than the traditional CTDs on core Argo floats. And therefore, to produce science quality data that the community can use, BGC float data has to be adjusted before it can be used for operational applications or research. And but in order to adjust the data, you first have to understand how a sensor drifts over time. To demonstrate how nitrate sensors drift, I'm going to show you some data from a profiling float that was deployed off of Hawaii. And this is a good float to use because we know from the Hawaii Ocean Time Series data that the surface nitrate is always zero no matter the time of year. So that provides a really convenient reference measurement that we can use to assess sensor drift. So this is a time series of what the float surface nitrate was over the course of about 3 years. So you can see that it started off around 0, but then over several years, the surface nitrate decreased about -2, so which indicates that the sensor is drifting low by several micromoles per kilogram. And if you plot the 1,000-meter nitrate data on top of this, you can see that the patterns of the surface nitrate and the 1,000-meter data are very, very coherent. And based on the hot data, we also know that the 1,000-meter nitrate data is very stable in this region as well. So what this implies is that the nitrate sensor is drifting the sensor drift is manifesting in an offset manner. So in other words, if the surface nitrate is reading low by 2 micromole per kilogram, then the 1,000-meter nitrate is also reading low by about 2 micromole per kilogram. So using this observation, we can correct both the surface and the 1,000-meter nitrate by forcing the surface nitrate to be 0 throughout the life of the float. So this is the corrected data. So the same offset was applied to the surface nitrate as to the deep. And as you can see that the 1,000-meter nitrate now hovers around about 42 micromoles per kilogram throughout the life of the float. And if you plot the 1,000-meter hot data on top of this, you can see that the float and the hot data are in very good agreement, especially in the first year. And in fact, they agree to better than about half a micromole per kilogram. And later in the float's life, the hot data and the float data tend to deviate, but that's probably because the float drifted away from Hawaii. So the discrepancy probably reflects real spatial differences between the float and bottle data. So anyways, what this float tells us is that the nitrate sensor can be should be adjusted by applying offsets. So basically, if you can figure out if the sensor is reading X micromole per kilogram high in one part of the profile, then we can apply an offset of X to the entire profile and get accurate nitrate measurements throughout. So this is the approach that we take to adjust nitrate data. So the key is figuring out how much nitrate is drifting, and then near Hawaii, we can use the surface as a reference measurement because we know that the surface nitrate is always 0, but that approach won't work for the rest of the world. So we have to take a different approach. The approach that we take is similar to how Core Argo adjusts for drift in their salinity data, and we take advantage of the fact that the deep ocean is stable and fairly predictable. So a profiling float makes measurements in the deep ocean, for each profile. So if we can predict the conditions in the deep ocean, then we can assess drift, sensor drift throughout the life of the float. And then for Core Argo, there are enough hydrographic and also historical Core Argo float salinity measurements that can be used to create regional climatologies to create this deep reference field that can be used to adjust salinity data. But unfortunately, for BGC floats, we don't have this luxury because, one, there's not enough hydrographic biogeochemical measurements to create these climatologies, nor are there enough historical BGC floats. So we have to take a slightly different approach. So to create these deep reference nitrate fields, we use global empirical algorithms such as LINER and CanyonB. These algorithms are trained using the GLODAP v2 data product and are capable of estimating nitrate very accurately, particularly in the deep ocean. So the inputs to these algorithms are temperature, salinity, oxygen, location, depth, and also date for CanyonB, which are all parameters that the profiling floats can measure, and the output is estimated nitrate with an accuracy better than half a micromole per kilogram below 1,000 meters. And this is fantastic because now we have an accurate reference nitrate field at depth that we can compare float nitrate measurements to assess sensor drift. So for every profile, we can now take the difference between the estimated nitrate from the algorithms and the measured nitrate from the floats to compute a nitrate anomaly. In this case, we do this at 1,500 meters to assess for sensor drift. So making the assumption that the estimated nitrate is accurate from the algorithms, then any patterns in this computed nitrate anomaly would represent sensor drift. So then we can use this nitrate anomaly as a basis to correct for sensor drift. So how do we actually implement this? To prevent over correction for the data, we don't adjust the data on a profile by profile basis, but rather we say, we expect some sort of random scatter of this nitrate anomaly, and as long as the nitrate anomaly stays within some confidence interval that we have set at plus or minus 1 micromole per kilogram, then we say that the sensor measurement is in agreement with the algorithm estimated nitrate, therefore no adjustment to the data is necessary. But once this nitrate anomaly starts to deviate significantly outside of these confidence intervals, then we need to apply a drift correction. And we do this by applying a linear drift correction. And basically, what that provides is, so remember the nitrate anomaly is basically the offset in nitrate that we need to apply to adjust the whole profile. So this provides a time-varying nitrate offset that we need to apply to correct the whole the data set. However, it's also not uncommon to see jumps in sensor performance like this. And therefore, in order to accommodate features like this, we take a piecewise linear regression approach where we linearly correct for sensor drift for different sections of the data set. So now that you know how we correct for sensor drift for nitrate sensors, what are some typical adjustments that are needed for nitrate floats? So this is a histogram that shows the magnitude of the offset or the nitrate adjustment that needs to be applied during the first adjustment and the second adjustment. So you can kind of interpret the blue as the first section of the data that needed to be corrected, and then the red as the second section of the data that needed to be corrected. And as you can see, that both corrections are centered around 0, but the first correction typically has a larger magnitude than the second one, which implies that the sensor performance, the sensor may have a larger offset when it's first deployed, but then it kind of stabilizes, and the second adjustment is smaller than the first. And the same pattern can be seen for the drift as well. So in the first year, the nitrate sensor tends to drift low by up to 5 micromole per kilogram per year. But then in year 2, the drift is now pretty much centered around 0, and the magnitude of the drift is much slower in year 2. So it seems like these nitrate sensors tend to drift more in the first year, but then it kind of stabilizes over time, which is great. So okay, so what does the data look like after all of these adjustments are made? And so one way we can validate that is by collecting discrete samples each time the profiling float is deployed. And this is exactly what the SOCOM project has done over the past 5 years. And so the SOCOM project has deployed over 200 floats equipped with nitrate sensors in the Southern Ocean. And for most float deployments, they collected bottle nitrate. So this is a plot that shows the bottle nitrate on the x-axis versus the float nitrate on the y-axis. So you can see very good agreement between the two measurements. The black line is the one-to-one line, and the dashed line is the Model 2 regression. So if you take the median residual between the float and the bottle nitrate, it's negative 0.12 plus or minus basically 1 micromole per kilogram. And some of this variability between the two nitrate measurements is due to real spatial temporal discrepancies between when the float made the measurement and when the bottles were collected. And this is because the float surfaces approximately 18 hours after it's deployed, and it can drift many kilometers away. So there is this spatial temporal discrepancy between when the float made the measurement and when the bottle sample was collected. And we make the assumption that about approximately half of this variability is due to real spatial temporal differences in nitrate, and therefore over the fleet-wide average, we assume that the accuracy is about half a micromole per kilogram, which is the same as the accuracy for the estimated nitrate from the algorithm. So this kind of makes sense. So our claim is that so far we believe that nitrate measurements from floats fleet-wide has an accuracy about half a micromole per kilogram. But this validation is on the first profile of the floats. So is there any evidence that support degradation of sensor performance over time? And the best way to analyze this or to assess this is to look at crossovers between GLODAP measurements and float measurements. So when we compare float measurements that are made within 20 kilometers of a GLODAP station, we can compute the residuals, which is shown here. And the top plot shows the residuals within the first 6 months of the float's life. And then this bottom one shows the residuals after the float has been deployed for at least 2 years. And you can see that there's no real significant difference between the difference within the first 6 months of the float's life versus after it's been deployed for at least 2 years. And based on these observations, these strongly suggest that there's no real significant degradation in sensor performance for nitrate for multiple years from these BGC flows, which is great news. So I want to end this talk by coming back to this animation that I showed you at the beginning. As you can see, the number of nitrate profiles have been steadily increasing in the past 10 years, and it will only continue to increase in the coming years. I also want to emphasize that nitrate data is adjusted in real time and made publicly available with no strings attached through the Argo data centers through the GoBGC program. So I highly recommend anyone who is interested to start looking at the data, start analyzing it, and start doing some really cool science with it, because this data set is for you guys, for the community. And the more people that use it, the more successful this program will be. And I hope that you learned something in this talk that will help you take advantage of this data set. And thank you very much for your attention, and thank you for your time.